Back from lunch. We're almost ready for our next talk. So if we could all quiet down a little beforehand, it would be great. Hey. Okay. It's about Rust. Shouldn't you all be excited? Okay. Daniel's going to talk about the case for a virtual Rust stateless codec driver. Daniel?
Okay. Can you guys hear me? Is the microphone working? For those of you who don't know me, which I assume is going to be the majority, my name is Daniel Almeida. I worked for Collabora for 3 years, mainly doing codec stuff, the interface between the streamer and the kernel. And as of recently, I've been working on doing decoders in Rust in user space. So now I'm fighting really hard to bring this to the kernel. And I'm halfway being hated by a lot of people, just kidding. So yes, I'm here today to talk about, the case for a virtual Rust stateless codec driver. I want everybody in the audience to really take a look at the title, because we're going to go piece by piece, every word that you guys see here, we're going to talk a little bit more about it. So I'm going to start with saying what a codec is and why we need codecs. Then I'm going to talk about hardware acceleration in codecs and why should we need that. After that, since now we have hardware, I'm going to talk about codec drivers, because now you have hardware to drive, so how do drivers work? Now that we have a driver, we need a way to talk to the driver, so I'm going to be speaking about the two major APIs in Visual Linux for you to be speaking to these drivers, the stateless and the stateful API. And after that, I'm going to talk about what is a virtual driver in this context, and about Visel, which is a virtual driver I wrote. And then lastly, I'm going to tie all of that back into Rust, and hopefully why we need Rust in this particular context. So without much further ado, let's get started. And the first thing I want to talk, as I said, is about codecs. What are codecs? Basically, codecs, they are a way for you to compress video data, because without codecs, we couldn't have video in the modern age. So if you have a 4K stream, for instance, and you do the math, like 3840 times 2160 times 3 bytes per pixel times 24 frames per second times 2 hours for a movie, this is going to be very huge. So in order for this to be even possible nowadays, you have to have a way to compress that. But thankfully, all video signals, they're full of exploitable redundancies. That's how video codecs work. They basically exploit these redundancies to shrink the amount of data that you have, therefore making, storing videos on your computer or streaming videos through the internet and a lot of other user cases even possible today. Usually this process is lossy. Right, so you can have lossless compression, but usually you lose a little bit of data. But the objective is to arrive at a passable approximation such that you don't notice that you've lost a whole lot of detail, hopefully, but you've shrunk the size of your image by a large amount. And for a given bit rate and power envelope, meaning for a given size of resulting file, the resulting file size, and for a given amount of heat that you're going to be generating or power that you're going to be consuming from the device. All right, so we want things to be fast and hopefully cool, right? Because nobody likes to be sitting on a laptop that's scorching hot, or you don't really want to be using a whole lot of power, and you want things to be fast. So what's the solution for this? Is to have a hardware accelerator, for instance. So hardware accelerators, they tend to be more power efficient and faster, and it frees up the main CPU so that your main CPU can, basically hopefully do other stuff. But they're usually less flexible because you usually only get what you synthesize into hardware most of the time, right? And you're not going to be synthesizing all the profiles for all the codecs. You're only going to be synthesizing a small subset, and well, you kind of this makes it a little bit less flexible than doing CPU encoding or decoding. And there's another key aspect of this. Now that you have hardware to drive, so now you need a driver. And you need an API to communicate with this driver. So you have now yet another piece that you have to have that you didn't need to have with a pure software/CPU approach. And to understand these drivers, we first have to have a brief look at what is inside a bitstream. Let's say you're watching something on YouTube or you've downloaded some video file on your PC. What exactly is in there? So basically we have two blocks in there. The most important thing actually is the data to decode, right? That's obviously the most important piece. So the data to decode, the actual compressed data, takes the most amount of space. But that's not everything that's inside there. We also have a small block called the metadata block. And what exactly is the metadata block? It's data that's not going to be actually decoded per se, but it's very fundamental because it controls the decoding process. So it's data that the decoder will be consuming in real time in ingesting that metadata to actually, in real time, decide how is the decoding process is going to look like for each and every frame. So as I was saying, this metadata controls the decoding process. It may dictate to the decoder how the decoder is going to decode a particular frame, in which case it will only apply for that particular frame. Or it can apply to multiple frames, depending on the kind of metadata we're speaking about. So like for MPEG decoders, you have like things like PPS and SPS and VPS, which are like metadata that stays for multiple frames. Or you can have metadata that's only for a single slice, which is only going to apply for that particular slice in that particular frame. And you also have the slice and or tile data, which is the data that you're going to be hopefully decompressing. So far, so good, I imagine. So how can we talk to these devices? Because if you will recall, now we have hard drive to drive. So now we need to talk to the device somehow. In Video for Linux, we basically have two different types of APIs that you can use in order to talk to the codec. One of them is the stateful API. I like to think of the stateful API as a black box. So you just send in this data to the device. The device will do its magic, quote unquote, and it will keep track of the metadata by itself. You don't need to do much. You just send in the data, and bam, hopefully you get decoded data back. Very interesting. If the stateful interface is a black box, I like to think of its opposite, the stateless API, as a clean slate. Meaning, for each and every frame, you in the user space have to extract that data, and then send that data together with the compressed data to the driver. And then the driver will use this metadata that you have just parsed and sent with the compressed data, and it will decompress the data. So if the stateful API is a black box, the stateless API is a clean slate. For each and every frame, you have to be submitting data that will tell the device how to operate, and then the device will basically forget about it, and then on the next frame, you have to submit the new metadata and the new compressed data for the device to decode, and so on and so forth. It doesn't really keep the state of the metadata within the device, hence the name stateless. I assume so far so good. So now we're going to be talking about virtual drivers. We have a virtual driver which I have written called Visel. And Visel is basically, as I said, a virtual stateless driver that just pretends it's decoding data. And why would a driver that just pretends that it's decoding data be useful? Most people may be asking. Well, it's useful as a developer aid, right? To help developers who are working on this particular niche to either develop new implementations or fix your broken implementation. Let's say you found a bug, you can use Visel to dump some debug data to help you fix the bug, because Visel is a driver that instead of decoding video, just dumps a bunch of data, useful debug data through debugfs, through ftrace, and through the Video for Linux test pattern generator. And what is Visel good for? As I said, it's good to help you to develop a new user-land application. Usually you have a working application, then you use that, you trace the working application, and you use the trace provided by Visel to develop a new one. That's one use case. Helps you fix bugs, helps you test your user space when you don't have hardware available. So if you don't have hardware that can decode a particular codec, you can still use Visel to test the GStreamer code, to test the FFmpeg code, to test the Chromium code, so on and so forth. And you can use Visel for prototyping. So far so good. Let's do a quick recap over here. I explained a little bit what codecs are, why we may need hardware acceleration. I said that when you use hardware acceleration, you're now going to have a driver. And to talk to this driver, you have two APIs. And now I said that we have in the media subsystem some virtual drivers, one of which is a virtual stateless codec driver. What is the problem? Well, the problem is this. Can you guys read this? It's readable in the slides, I think. So what is this? this is what you find when you open up a codec specification. I think that this is for AV1, which is the state-of-the-art codec. And this is how you parse this thing. This is how you extract the data from the bit stream to send the data to a stateless codec. Because as I said, a stateless codec needs the metadata to decode each and every single frame. So in user space, you have to go through everything in here and start parsing. And right from the outset, I see a few issues over here. So we are reading, there's on the second column, there's F, and in parentheses, there's a particular number. That's the number of bits that you're going to be reading for that particular syntax. Now, what happens if you have a bug? If you were to read, for instance, there's a type over there which says show existing frame, and you have to read a single bit from the bit stream in order to get the value for this. Let's say that instead of reading, say, 1 or 2, you read false because you had a bug, whatever. So now that branch, so show existing frame, is not taken because you had a bug in your implementation. And if that branch is not taken, now you're out of sync with the entire thing. So now you're going to be reading like, instead of reading frame to show map IDX, which would be the next field, you're now reading frame type. Let's say that you were to read all that stuff and eventually read that return over there, but you didn't because you missed this branch because you read that thing over there wrongly for whatever bug. So now, instead of returning, you're reading everything, thereby reading over the memory that you had in the first place. If you had that return over there, you would have only a given amount of memory, but you missed it because you had a bug, and now you're reading more stuff, thereby reading after the end of the memory. This is a crash at the best of scenarios. At worst, it's, you can corrupt stuff. This can go very badly. So this is very tricky, and this is very indented. You can see that whenever you see a pair of parentheses, this is like yet another syntax element that will have its own way to be parsed, and you can have if statements and for loops, and etc. It can have other things with parentheses, which means yet more indentation, basically. So this can get very hairy, very tricky, very fast. And you have pages and pages of this. I'm pretty sure that you have at least 20 pages of this stuff to parse just to send that to the driver. So this can get very complicated, and not only can this be very complex, but we're also reading in the indexes for arrays, and we're also reading a few loop variables directly from the bit stream. So if we go back a little bit, let me see if I can find it from here. Yeah, so frame to show map IDX you're reading that from the bit stream, and you're using that to index into another bit of memory, which is the ref frame type array. And if you read that index wrong, now you're indexing into an array with the wrong index, and as we all know C here, I assume, we know that this can be very broken very fast. So yes, this is very hairy. So here is my pitch. Here is my pitch to use Rust. We're handling a whole lot of metadata per frame, as I said, a whole bunch of data that we're getting from user space. And although we do some vetting of that in the kernel, there's some functions in the kernel aimed at potentially detecting invalid input from user space. They're not, that foolproof. And the attack surface here is so huge that no amount of ad hoc and kernel validation would ever catch all the possible ways in which this can blow in your face. This metadata thing is very structured and very complex. The meaning of fields can change based on the value of other fields. As I said, if you read true, then go here. Otherwise, take the other branch. This can get very complicated as well. And you also have to maybe juggle between multiple versions of the same metadata. For instance, in HEVC, you can have multiple instances of a VPS or a PPS or a SPS, which you have parsed previously, but of which only one is active. So you have to juggle between multiple of these, and only one is active at a time. So there's plenty of pitfalls that you can sort of shoot yourself in the face when doing this. And the problem is exacerbated in real drivers, because as you will recall, so far we have been talking about VIs, all about virtual drivers, and if that thing crashes, it's bad.
but it's not the end of the world, although it's very bad. But in a real driver, you may use this broken metadata that you're sending to the driver and use this broken metadata to program the device. So now you may be changing the decoding process of the device, and who knows which ways. You can hang the device at best or corrupt the state of the system at worst, and you may even have to reboot the system. It has happened to me multiple times that I had some bug somewhere and I had to reboot the machine in order to, because the device was stuck, basically. So I assume by now you guys can see that we have value in having Rust here, because most of what I have spoken about is check that compile time when you have Rust. So when you have Rust, you have memory safety. If you basically, all the issues I was talking about accessing invalid memory, by default are prevented in Rust at compile time. You have just fixed yourself a bunch of different classes of bugs for free, just by switching the language. And I was speaking about virtual drivers all this time, and about Visel in particular, which is a virtual driver for testing codec drivers and codec user space, because I think virtual drivers are the perfect candidates to experiment. And Visel in particular is a perfect candidate to be rewritten in Rust. And we can make that even simpler, because Visel has a bunch of ftrace code and debugfs code, and we don't need any of that. We can strip away basically all these things for now and just have a virtual driver that boots and that can pretend that it's decoding data without dumping debug data to user space. We don't need that in the first version of a Rust driver in Video for Linux. And I think the most important part of my pitch is if we make a virtual driver in Rust and we make it work and we prove to everybody that this thing is working, it's not much more work to get a driver for real hardware. Because then only the parts that touches the real hardware, like getting DMAs and getting interrupts working and blah, 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 these pieces of the kernel, they're basically being worked by everybody else, because everybody else who's interacting with hardware have the same issues to fix. So they're also working on this. So if we come up with a Video for Linux 2 specific bits, maybe in 6 months or 1 year, the situation of Rust in the kernel will be more advanced. Therefore, we will have more abstractions for more areas of the kernel. Therefore, it will be easier to write a driver for real hardware. We'll have the Video for Linux bits, and we can hopefully profit from the work that other people have done in other areas of the kernel. So I have been trying to do this for 6 months or 1 year, I think. I have sent to the mailing list a sample Video for Linux 2 driver. And what we have in this driver so far, we have the abstractions for a few of the Video for Linux 2 data types. You have a very thin VB2 abstraction from which you can spawn a queue to share memory, share buffers between user space and the driver. We have abstractions for some of the Video for Linux 2 ioctls, not all of them. We have the necessary code to get the driver to probe, because believe it or not, it's actually complicated to get a Rust driver to probe on the kernel. There's a proc macro going on in the background, blah, blah, blah. So we also have the code to get the driver to probe, which is in and of itself is an achievement, I think. And we have a simple module. And what does the simple module does? It basically boots, it probes. And whenever an ioctl is called by user space, it just prints, hey, this ioctl is being called. I am able to process this ioctl in Rust. I'm able to translate all the arguments into Rust. And it basically returns. It's just prints something to make sure that this ioctl translation layer between C and Rust is working. And from this, we can start to add functionality to the driver, so that when it actually processes the ioctls, it stores states and actually carries out what the ioctl is supposed to do. And what do we need in order to get this thing going? We need support in Rust for referral-to control, so that we can send the metadata to the driver. We need support for some media controller bits, so that we can have referral-to requests, which is a way to tie this metadata to a particular frame. So we need Rust support for this in order to get stateless codecs to work in Rust. We need M2M support for device run and friends, which is just a framework who's scheduling the decode jobs in the kernel and deciding when a job should run in the hardware, and we need more ioctl support because we only have support for a few ioctls and a real driver needs much more. And most importantly, we're still waiting for the green lights from the maintainers. I have been talking to a whole lot of maintainers. I've been to the media summit. Some of the maintainers I think are in this room or not. I don't see them. But anyways, I got some feedback from them, and I think this summarizes it. In Virtual Linux nowadays, the state of the subsystem is that the subsystem is a little bit overwhelmed. There's a bunch of patches being submitted. There's not enough people to review. And basically, people are overwhelmed, and nobody really has the time to have yet another language in the subsystem, which I understand. This is a completely valid thing to say. So there's not enough reviewers, not enough maintainers. Some C frameworks, like the media controller, have some long-standing problems which nobody has fixed yet. So one of the feedbacks I got was like, hey, maybe these issues should be fixed in C before we add yet another language, which is some valid feedback. I agree. There's a huge fear of breaking C code, which is impossible. Just by how this works, you're never modifying the C code. So this can never break whatever C code is already in the kernel, I promise. And the other issue is who is going to maintain this layer, because one of the feedbacks I got was like, hey, if I change something in the C layer and just break the Rust code, who's responsible for keeping these two things in sync and fixing the Rust code, which again is a very valid argument to have. But we, as Collabora, we want to unblock this effort, which is why we have been investing in the media subsystem. We're investing in CI, and we're trying to change a little bit how maintainership in the Virtual2 community works. We're trying to get it more like GRM, where you have multiple commuters and where you can share the workload. So we are doing what we can in order to alleviate some of the issues so that we can proceed with this effort. Which is why we're proposing this virtual driver, because we think that this is a good candidate for experimentation. This is not the scheduler or memory management or anything in which if you break that, you've broken the entire kernel. This is just a virtual driver. If it's broken, it's not going to be a huge deal. So summary here, stateless drivers, they take a whole bunch of untrusted data from user space. This can get hairy. This can let you shoot yourself in the foot very easily. So the surface, the attack surface is enormous, and Rust is a perfect candidate to fix that at compile time, we think. And Visel virtual driver is a prime candidate to experiment in Rust and to be rewritten in Rust, in our humble opinion, or in my humble opinion. And this is what I had to say to you guys today, and hopefully this was interesting for you. Questions? Yes, sir.
Hi, thank you for the talk. So I have very rough understanding of Rust, but I would like to get more idea how Rust would protect us from part of the issues that you described. So I understand how it protects us from accessing past the size of the array, but in case when you have like the metadata, it changes because of the previous values that you are parsing, right? Mm-hmm. How Rust would protect us from misinterpreting that new piece of data?
Well, if you get metadata that's broken, and this broken metadata leads you to access another part of memory which is invalid, that just panics, basically. So that's not like, in C you can dereference any value you want, but in Rust you basically can't. You panic. And then you compare that with the user space Rust implementation to also make sure that you're getting sanitized data.
So basically the only thing that, the only protection that we get is that we will not access array that is out of bounds, basically. Because,
we can actually handle cleanly these access.
Okay, so tell me more.
We can have a clean exit with that bad access.
Okay, so what's the benefit I mean, you can always define a C function, right? That will check the size of the array, how much data is there left, and never access the buffer directly just through that function. That will always check if you are not out of bounds.
You can.
So then,
The human factor.
Yeah.
You're forgetting the human factor.
of course, yes.
So
But
it
then,
can,
the
but you
amount of
won't.
work that is there to like add the whole Rust bindings. I'm not saying it's bad, right?
Yeah.
I'm just trying to wade in the adding a single function that you can use to access the metadata, the buffer that you have metadata in, and porting the whole thing to Rust.
I can give you another example, which is like error handling in Rust, for instance, is much better. So while in C, if you get something, a wrong metadata, you may fail, and then you may have a bunch of go-tos that you have to go back in the exact reverse order, blah, blah, blah. In Rust, that's free. The compiler just wires up the calls from you in the right order, always. So you can never forget to clean up after you're done, if you have an error, you know? And you can say, well, you can just define your go-tos in the right way and be careful. Yes, C is just fine, hence why we have drivers in C working. But as humans, we can forget, you know? So it's just a way to, you know, kind of close in on the human error factor, I'd say.
Might
Any
sound
more
like
questions? Questions?
Yeah, I was wondering, if you were theoretically to transpile your Rust to C, would that be acceptable then?
To transpile to C?
Yeah.
I'm not aware of any way to transpile Rust to C, but you can have a C API for Rust, somewhat easily. So you can define a header file, and you can ask the Rust compiler to provide you with C linkage, C API, so that you can have a C API for your Rust code in the kernel even.
No, the idea was that your code is being rejected because it's Rust and not C.
I'm sorry?
You said earlier in your slide that the maintainers reject your code because it's written in Rust.
Yeah.
But if you wrote Rust and transpiled to C and submitted the C result, would that make them happy?
Yes, that's not really how it works. You can have a C API to your Rust code, but you're not transpiling it and sending C code only. It's just not how the process works, you know. So we're not speaking the same thing. You're speaking about transpiling, but I'm speaking of having native Rust code and offering as well a C API to that Rust code. And I am not aware of any way for you to transpile Rust directly into C. And only send the C code as you're proposing.
Okay, I think we're out of time. I think so. Thanks so much for your talk.